Welcome to lecture 18, our final session for this unit. Today we will synthesize all hardware components discussed earlier by tracing the complete optical paths of both the fluorometers and spectrofluorometer. Let us begin with the typical commercial filter fluorometer. Carefully follow the path of the photons. At the top we have primary excitation source, usually a mercury vapor lamp. In these cost effective instruments, the intense multiline light travels downward and first passes through a mechanical shutter. This shutter allows the operator to completely block the beam to measure detector dark current. Next, the light passes through a sample aperture disc and encounters optical lenses labeled A and B. These lenses collimate the beam, focuses the light. Immediately afterward, the beam reaches the primary filter. This filter transmits only the desired excitation wavelength while blocking all others. Now we observe the key stability feature. Just before reaching the sample, a small mirror intercepts a fraction of the incoming light. This becomes the reference beam. The intercepted light passes through a beam attenuator, reducing its intensity so it matches the weak fluorescence signal. It then enters a dedicated reference photomultiplier tube. Meanwhile, most of the beam continues forward to the sample cuvette. The molecules absorb light and emit fluorescence in all the directions. Notice the right angle geometry at 90 degrees and secondary lens systems collect the emitted light. A secondary filter then passes fluorescence wavelengths and blocks scattered excitation light. The purified signal reaches the sample photomultiplier tube. Electronics compute sample signal divided by reference signal because both beams originate from the same lamp. Intensity fluctuations cancel out, producing stable measurements. Filter fluorometers are therefore compact, mechanically rugged and cost effective. An architecture of spectrofluorometer in which we will upgrade to the two spectrofluorometer. The most obvious difference, no simple optical filters. Instead, the instrument uses two motorized grating monochromators, first for excitation and second for emission. The radiation source is typically a high pressure xenon arc lamp. This lamp produces an intense continuous spectrum. Broad white light enters the excitation monochromator sheet. Inside, a diffraction grating disperses light into individual wavelengths. A narrow selected band exits the encounter a beam splitter. The beam splitter again creates electronic stability. A small portion of excitation light is directed to a reference detector. Because xenon intensity varies with the wavelength, an absorbance compensating cell or quantum counter may be placed before the reference detector. The main beam continues into the sample compartment. Fluorescence emitted at right angles is collected and directed into the entrance slit of the emission monochromator. A second diffraction grating disperses the emitted light, allowing wavelength scanning. Selected emission wavelengths finally reach the sample photomultiplier tube. Two independently scanned gratings allow continuous excitation spectra, continuous emission spectra, high spectral resolution. However, raw spectra vary between instruments due to detector response and grating characteristics. Therefore, software correction generates instrument independent spectra. Modern spectroscopy goes beyond intensity. We also measure fluorescence lifetime. After excitation, emission does not occur instantly. There is finite delay, the excited state lifetime. Measuring these lifetime measurements reveals collisional deactivation rates, energy transfer processes, and excited state reactions. Lifetime analysis also allows separation of overlapping emissions if different species decay at different rates. Historically, only phosphorescence lifetimes could be measured easily because they were slow. Modern pulsed lasers and ultra-fast electronics now measure fluorescence lifetimes from 10 raised to minus 5 to 10 raised to minus 9 seconds. Two main techniques are used: time domain method, in which a pulse excitation source directly measures exponential decay versus time, whereas second method is frequency domain method. A sinusoidally modulated source produces emission with phase shift and reduced modulation depth. Mathematical analysis of this shift yields the lifetime. Modern research instruments often support both approaches. To conclude this unit, we recognize that luminescence principles drive major modern technologies. The most common example is the light emitting diode or LED. LED operate via electroluminescence, where electrons and holes recombine across a semiconductor band gap to emit photons. We also engineer phosphors, crystalline materials doped with rare earth ions that emit visible light under high energy excitation. In harsh environments, phosphor thermometry measures temperature remotely using lifetime changes. In archaeology and geology, thermoluminescence dating determines the age of ceramics and minerals by measuring stored radiation energy. In nuclear medicine, thermoluminescent dosimeters or TLDs measure the cumulative radiation exposure through emitted light during heating. These applications demonstrate that luminescence is not abstract theory, it is a foundational mechanism behind modern technology. This officially concludes this unit. In our next lecture, we will begin with next unit, that is vibrational spectroscopy. Thank you for your attention.